Good day, everyone. My name is Patric Bettati, and I'm currently an undergraduate research assistant entering into my senior year at the University of Texas at Dallas, working in the quantitative bioimaging laboratory under supervisor Dr. Bao Fei. My project is titled Augmented Reality Assisted Biopsy of Prostate Lesions, but before delving too deeply into the subject, allow me to provide some quick background information on the various aspects of the project. Augmented reality, or AR, is an interactive computer-generated experience where the user is able to interact with or visualize 2- or 3-dimensional images displayed over the real world. One method of using AR is for the user to wear a headset which displays all augmented reality data over the user's eyes, allowing them to see virtual images superimposed on the real world. In this project, we use the Microsoft HoloLens 2 to display and interact with our augmented reality data due to its lightweight construction, robust processing power, and wireless capability. In the US, prostate cancer has been found to be the second leading cause of cancer death in men, making it a key area to develop novel techniques. Moving on, biopsies are when a needle is inserted into the lesion of interest within a patient with the purpose of tissue removal in order to better diagnose the patient. For prostate biopsies, the small volume of the organ as well as its deep location within the patient make it difficult to consistently remove lesion samples, often requiring multiple biopsy attempts. Additionally, the challenges involved with prostate biopsies often require the use of an intraoperative imaging technique, generally ultrasound. It must be said, however, that ultrasound images are typically unable to differentiate between healthy prostate tissue and the tissue of the lesion. In this project, our objective is to use preoperative CT images to locate, localize, and digitally segment out any lesions and additional models of interest present prior to the operation. We then plan to use these obtained 3D segmentations in conjunction with intraoperative ultrasound data to register the lesion onto the ultrasound data in real time. Once this is accomplished, we plan to project this registered real-time data through the HoloLens 2 AR headset, theoretically resulting in a multimodality, real-time, interactive augmented reality system. Our workflow consists of 5 main steps: data acquisition and segmentation, hologram scripting, HoloLens 2 user interface system, real-world registration, and finally the addition of real-time ultrasound data to the scene. The first step begins with the patient undergoing routine CT imaging for diagnosis. The next step is the automatic or manual segmentation of various models of interest, such as the lesion, the prostate, the skin, the bones, etc. These are all then loaded into Unity, a visualization and game design software. We are then able to move into the next step of our workflow. Here, we write Unity scripts in C# to code the holograms to react in certain ways to stimuli. Examples of scripts are the ability to manipulate the holograms with your hands or to institute voice commands to the holograms. We are also developing a user interface system in order to provide more customizability to the physician. This would give the physician greater control over the holograms during system use, eradicating the need for the physician to learn any additional software such as Unity. Examples of UI abilities are transparency changes, and hologram collision color changes. However, the virtual holograms require some kind of anchor in order to display them in the correct area in the real world. We had great success when using the Vuforia software in conjunction with 2D paper imaging trackers to do this. We also attempted to add 3D Vuforia trackers, potentially allowing us to use cylindrical or cuboidal trackers to provide the same function as the 2D trackers, but also opening up multiple angles. The 3D trackers, although promising, currently can only be used for static holograms that do not need to move in the virtual world. Finally, we also plan to incorporate real-time ultrasound data into the Unity scene in order to provide the physician with all the data needed in the virtual world. We plan to display our segmentation on top of the ultrasound data as shown in the image to provide both segmentation as well as ultrasound data in the same place. This step is currently still in progress as there are a few limitations within the HoloLens 2 for displaying real-time data. Moving on to our results, we can provide multiple methods of manipulating holograms, either using real-world markers or simply through manual manipulation of the holograms. Using these, as well as a few scripts allowing color change upon collision, we can provide the physician with visual cues for when holograms collide or interact. If they are properly registered to their real-world counterparts, this would allow the physician to more easily determine the correct biopsy location on each individual patient. To finish, we submit the plans and foundation for a multimodal real-time augmented reality system for use in prostate biopsy operations. Our systems would be very variable and usable with most preoperative imaging modalities, as well as allow for physicians to maintain spatial awareness at all times. The focus on this project from here would be to create a channel for real-time ultrasound data to be displayed through the HoloLens 2 within Unity. We must also state that the current registration model of Vuforia markers would likely be unwieldy, and we remain on the lookout for differing registration techniques. Thank you for your time and attention.